Hello, I am Alfonso, Doctor in Pure Math. In this video, we will see one of the most important distributions, the normal distribution, also called the Gaussian, named after Gauss, the prince of mathematics. We will start from the Gaussian function, which has this formula and this graph. It satisfies this property, which then we can think of it as a probability density function. This is saying that there are more chances to see something around 0 than far from 0. Now I want to show you why this distribution is so important. For that, let us record the following. In Python, we can generate a virtual data from a distribution. For example, here we have a fake data for a Poisson distribution. As we know, the expected value here is 1 for the Poisson distribution. Nevertheless, if we take the mean of the data that we generated, the number can change. This new expected value from the data is not necessarily 1. Now we see here in different examples different numbers. Our intuition tells us that if we increase the data set, we will get closer and closer to the real mean. Here in Python, we can see that indeed this is the case. But let us see if we can support this intuition with math. We can think each element in our dataset as a random variable, say y1, y2, and so on until yn. Each of these random variables is independent and has the same probability mass function, the same expected value that we call mu, and the same variance that we will call sigma square. Then for the mean is given by this formula. This mean is another random variable. We can change the number n for any other number, and what we will prove is that if we make this n go to infinity, we will have the constant mu. For this, we calculate the mean of the mean, and we get that it's equal to mu, to the mean. Then we calculate the variance of this, and as we know, the variance is quadratic, so this n here goes as n squared. Then we know that each of the variables is independent, so the variance of this sum is the sum of the variance. Then we know that each of them have the same probability mass function, therefore the same variance, which is sigma squared. So we have n times sigma squared. And then by canceling 1n with 1n, we get that this is sigma squared over n. If we make n go to infinity, this variance goes to 0. And if the variance is 0, then our random variable is a constant number. And which constant number it will be? Well, exactly the same as mu. After seeing this calculus, we can play with this random variable, the mean of a data sample, changing it a bit, as you can see here. And what we get here, when n is equal to infinity, will be a random variable whose mean is 0 and whose variance is equal to 1. The central limit theorem says that the probability density function of this new random variable when n is going to infinity is a Jaws-sian function. So we can think that what the Gaussian or Jaws-sian function models is the probability density function of one of these sets when n goes to infinity. One important thing to notice is that this set is for any y, any kind of function. You can put the Poisson distribution, the hypergeometric distribution, the binomial distribution, any distribution that you have in mind. You make these sets from a data set, and when you make n go to infinity, it will be modeled by a Gaussian. So the Gaussian is eating everything that has this form. Let us see some of this with a Python experiment. So this code plots measurements for set n for different distributions. such as the Poisson distribution, the hypergeometric distribution, and the binomial distribution. It depends on what I write here. Here below you can see the full code. If you want, you can get a screenshot of it. Now let's plot set n for n equal to 2. As you can see, it doesn't look as much as a normal distribution. Now we change to binomial. It looks a bit better. For hypergeometric. Now let's increase the number n.